Welcome to the 15th tutorial in the GPSX tutorial series using Python to simulate random events. When constructing a model, we often rely heavily on historic data for testing plant performance, making it easy to overlook that there is often a degree of randomness to system inputs. Some data may also be unavailable or infrequently collected, requiring the use of average conditions, which could potentially introduce an input bias to our system. By using Python, you can introduce reasonable random inputs to your system to simulate unknown operating conditions and simulate random events such as a storm's severity and frequency. This will allow you to see how your plant will be impacted by a random event. The goal of this tutorial is to show users how the random number generator in Python can be used to simulate random events in GPSX. Please note that a Pro Plus license is required for Python scripting integration in GPSX. Begin by opening a new layout and save it with an appropriate name. Add the following objects to the drawing board: a wastewater influent object and a stormwater influent object from the Influent tab of the Process table, a two-flow combiner from the Flow Combiners and Splitters tab of the Process table, a plug flow tank from the Suspended Growth Processes tab of the Process table, a circular secondary clarifier from the Secondary Clarifiers tab of the Process table, and a wastewater outfall object from the Effluent tab of the Process table. Ensure the comprehensive Mantis 2 library is selected in the Library drop-down menu. Next, verify that the objects on the drawing board are using the correct models. Check that the wastewater influent object is using the COD states model. The stormwater runoff object is using the runoff model. The plug flow tank is using the Mantis 2 model. And the clarifier is using the simple 1D model. Connect the streams as shown. Relabel the processes appropriately. Change the influent object process label to influent and the influent stream label to WW. Change the stormwater runoff object process label to rainwater and the influent stream label to rain. Change the two-flow combiner process label to influent combiner and the output stream label to mixinf. Change the plug flow tank object process label to aeration tank, the overflow stream label to MLSS, the pump stream label to PMP, and the recycle stream label to RAS. Change the secondary clarifier process label to final clarifier, the overflow stream label to FE1, and the pump stream label to WAS. Change the wastewater outfall object process label to effluent. Save the layout. Switch to simulation mode. Create a new output graph for the flow leaving the influent combiner, which can be found by right-clicking on the influent combiner and selecting Output Variables Flow. Rename the plot to Total Influent and set the axes to auto scale. A Python script has been included in the GPSX installation to be used in this part of the tutorial. Locate the GPSX installation on your machine and navigate to Layouts, Tutorials. Locate the Tutorial 15 random Python script and open it. Save the script in the current working directory. Select the Tools drop-down menu from the main toolbar and select the Python Script Manager. Add the script to the Python Script Manager by pressing the Add button. Select the pre-built script and press Open. Press the Edit button to open the script in Notepad. We will now take a look at what the script is doing. The script has two distinct sections, user inputs and functions. In the user inputs section, there are various user-defined variables. The rain inflow variable is a list of values that correspond to various possible rainfall depths to be generated by the stormwater influent object. There are also values that will be used to define the stop time and communication interval. The other section is the functions section, where the 4 functions included in the Python script generated by GPSX are contained. The start function uses a new GPSX recognized Python command, GPSX set cint. This command allows you to change the communication interval used in the simulation and only requires you to enter the new communication interval. We are introducing randomness to our simulation in the cint function. The Python random library is used to generate a random integer value between 1 and 100. Depending on the value of the random number, a value from our rain inflow is assigned to the rainfall depth input variable in GPSX using conditional formatting in Python. It is also important to note that a count variable is used in this section. This variable is updated at each communication interval and tracks the elapsed time. Each time the count equals 1, which corresponds to 1 day being elapsed, the value of count is reset and a new value is assigned to the rainfall depth influent parameter based on the value of the random number. Save the Python script. Press the Run button in the Python script manager to run the script and observe the results in the output graph. Note that your results will be different due to the inputs being randomly selected. As a means to control the amount of flow entering our bioreactor, we will now add a control splitter to our model to act as a bypass weir. This will allow us to preserve the operation of our bioreactors during a wet weather event. Switch to modeling mode. From the flow combiners and splitters section of the process table, add a control splitter and a 2-flow combiner to the drawing board. Connect the streams as shown. Relabel the 2 new objects. Change the process label of the control splitter to bypass, the overflow stream label to WWINF, and the pump stream label to bypass. Change the 2-flow combiner output stream label to final F. Switch to simulation mode. Create a new output graph tab. Create a new output graph with the following output variables. The total influent flow, which can be found by right-clicking on the influent combiner and selecting Output Variables Flow. The aerator flow, which can be found by right-clicking on the bypass object WWINF connection point and selecting Output Variables Flow. The bypass flow, which can be found by right-clicking on the bypass object's bypass connection point and selecting Output Variables Flow. Rename the plot Influent Bypass Operation and set the axes to autoscale. Open the Python script manager. We will be editing the Tutorial 15 random Python script. Select it in the Python script manager and press the Edit button. Save the script with the new name. Add the following code to the script. To the user input section, we will be adding a variable called max aerator flow. This will specify the maximum flow rate that can be sent to the aeration tank. We will also be adding an if-else block to the cint section. This block will be controlling the amount of influent that is bypassing the aeration tank. It checks to see if the influent is greater than our maximum allowable influent, and if it is, it bypasses the excess influent flow. Save the script. Add the script to the Python script manager by pressing the Add button. In the Python script manager, press the Run Script button. Notice in the output plot that each time the total influent flow exceeds our aeration tank influent limit of 4,000 meters cubed per day, the excess flow is bypassed to ensure that the limit is not exceeded. Remember that the inputs in this script are randomly generated, so your plot will look different than the one in the video. While the changes in the simulation occur instantaneously, that may not be the case in the real world, as it takes time to send the signal and start the pumping equipment. To address this, we will look at how we can introduce a delayed response with Python. A script has already been created for use in this section of the tutorial. Locate the GPSX installation on your machine and navigate to Layouts, Tutorials. Open the Python script titled Tutorial 15 Delay. Save the script in the current working directory. Open the Python script manager. Add the new script to the Python script manager. Select the script in the Python script manager and press the Edit button. We will now look at how this script has been changed from the Tutorial 15 bypass script. In the user input section, we have added a list variable called influent. The current influent flow rate will be collected at every communication interval and be appended to this list. In the functions section, we have modified the try except block that we had created in the Tutorial 15 bypass script. Now the try except block is looking at the influent flow rate that occurred 5 communication intervals prior rather than the current influent flow rate. This introduces a delay of 5 communication intervals between the maximum aeration tank influent value being exceeded and the control splitter taking the appropriate actions. Save the script. Press the Run Script button in the Python script manager. In the output plot, you will see that when the aeration limit is exceeded, the bypass is not immediately activated, but rather the excess flow continues to enter the aeration tank. It can also be noticed that there is a delay in reducing the bypass after the system begins to return to normal operating conditions. This results in excessive flow being bypassed as the system recovers. Save the layout. You have now completed the 15th tutorial in the GPSX tutorial series. You should now be familiar with how Python can be used with GPSX to introduce random events and delayed actions.